As a second example of a cumulative area function, let's see if we can find out what a formula for the integral from 0 to x of t squared dt. Once again, the name of our horizontal axis is t. The function we're working with is f of t equals t squared, so y equals t squared, which is a parabola. And we want the area underneath that parabola between 0 and x on the t-axis. Now, since this isn't a familiar geometric shape, we're going to have to use Riemann sums. So let's figure out Riemann sums, making sure that we're using t's in the appropriate places. So for example, when we break this up into n equal rectangles, or n rectangles of equal width, then the width of each rectangle I'll be writing as delta t, since I'm using the t-axis here. And that will be the right endpoint minus the left endpoint. So x minus 0 divided by n. So my function is f of t equals t squared, and my interval from a to b is from 0 to x. So that's b minus a over n. The formula for t sub I, using the right endpoint, is a plus delta t times I. The left endpoint is 0. Delta t is x over n times I. So my formula for t sub I is x over n times I. So the height of that rectangle, f of t sub I, is going to be t sub I squared, which is x over n times I squared. So x squared over n squared I squared. So the delta t represents the base or width of rectangle r sub I. Remember that this represents the height of r sub I. So to get the area of r sub I have to take the height times the base. So f of x sub I multiplied by delta x. So that's x squared over n squared I squared multiplied by x over n. So that gives me x cubed over n cubed I squared. So that's where we are so far. Now that's the area of just one rectangle. If I want the total area of all n rectangles, then I need to form the Riemann sum I equals 1 to n of f of x sub I delta x. So that's the sum I equals 1 to n of x cubed over n cubed times I squared. So that Riemann sum is equal to factoring the x squared over n cubed, x cubed over n cubed out front. And then the value of this integral is going to be the limit of this as n goes to infinity. So first of all, let's substitute in our summation formula for the I squared. We'll get x cubed over n cubed times n plus 1 times 2n plus 1 over 6. We can simplify by canceling an n to get x cubed times 2n squared plus 3n plus 1 all over 6n squared. And finally, we'll let the number of rectangles go to infinity by letting n go to infinity. So the integral from 0 to x of t squared is going to be the limit as n goes to infinity of this Riemann sum. Notice that it's n which is changing, so the x cubed is treated as a constant. This rational function is balanced, the degrees are the same, so the limit is going to be the ratio of the leading coefficients. So I get x cubed times 2/6, which is the same as 1/3 x cubed. So let me summarize the two cumulative area functions that we figured out so far. We found that the integral from 0 to x of t dt is equal to 1/2 x squared. And we saw that the integral from 0 to x of t squared dt, which is the one we just got, was 1/3 x cubed. So I'd be interested to hear your prediction for what the integral of t cubed from 0 to x will be. If you're guessing 1/4 x to the 4th, then you are right, and you're actually onto one part of what the fundamental theorem of calculus says. And that's what we'll be exploring in the next videos.